Solving systems of equations in two variables using linear combinations, also known as elimination. Recall that the solution to a system is the point or points where the lines intersect. In this case, I am unable to read the exact point off the graph because my coordinates are not integers, so I need to use one of my algebraic methods, either substitution or elimination. In this video, I will use elimination, which is also called linear combinations. Your paper might not look exactly like mine, but you can always write these notes on separate paper if it doesn't. The steps to elimination are essentially to line up the equations on top of each other so that the equal signs are lined up and the like terms are above each other. Create an additive inverse by multiplying one or both equations by a constant to create an additive inverse for one of the variables in the two equations. Combine the equations, and because we have an additive inverse, one of our variables will cancel out, or both. And then once we find one of our variables, like the x-coordinate or the y-coordinate, we can then solve for the other. This will make more sense when we do it. First, you need to understand what the word additive inverse means. Additive inverses are terms that add to zero. In other words, they're opposites. So for example, 3 and negative 3 would add to 0, so they're additive inverses. Negative 2x and 2x are also additive inverses. This example would be considered a level 1 example. It's a level 1 example because we already have an additive inverse. So our first step is to line up our two equations vertically above one another. So I have 2x plus 3y equals 13 and 5x minus 3y equals negative 20. I lined up my like terms above one another. Now I can add my two equations together. The reason why I will do that is because I know that 3y and negative 3y are additive inverses. So when I add these equations together, I get 7x equals negative 7. My y's canceled. When I solve this, I get x equals negative 1. Now I know half of my solution, because my solution is always x comma y, so I know it will be negative 1 something. I now take my value for x and substitute it into one of my original equations in order to find what y is. So I have 2 times my negative 1 that I now found plus 3y equals 13. And I'll solve this to get y equals 5. That means that my solution is negative 1, 5. That means that these two lines, if they were graphed, cross at one point, and that intersection point is negative 1, 5. Each of these lines has an infinite number of solutions, but the only solution to the system, or the only point that is on both lines, is this point here. Now, it's good practice to always check your solution in both equations. So I'm going to substitute my x-coordinate and my y-coordinate into both of my equations and check that they both come out true. Since both equations came out true, I'm confident that I solved the system correctly. Here's another example. So once again, I'm going to line up my equations vertically above one another, lining up my like terms. So I have 18x plus 3y equals 27, and I have negative 2x plus y equals negative 7. Since I wanted this y to be on the other side, I had to add y to both sides, so it switched to a positive. Now, the reason that this is a level 2 is that I see that if I add my equations together, I'll have a 16x and a 4y. Neither of my variables have canceled out. So I need to multiply every term in one of my equations by a number in order to get there to be an additive inverse. I'm going to choose to multiply every term by negative 3 so that I have a 3y and a negative 3y. I could have also chosen to multiply every term by 9 so that I would have an 18x and a negative 18x. And one thing that you might notice is I actually could have divided every term here by 3 at the start, and then I would use those numbers to create an additive inverse. There are lots of different ways to reach the correct solution. Now that I've written out my two equations, I'm going to add them together. That gives me 24x plus 0y equals 48. And when I divide both sides by 24, I get x equals 2. I need to take this value and put it into one of my original equations to solve for y. Now this value of 2 should work in my original equations and these equations and these equations, but we want to put it into an original in case we made a mistake moving a term to the other side or with our multiplication. And when I solved, I got y equals 3. This means that my solution is 2, negative 3, and I should check this in both of my equations to make sure that my solution works in both equations to ensure that it is the point of intersection. I've checked them. It works. I'm going to do one final example with you today. If you're on the paper that I am, I skipped example 3 because it was similar to example 2. And I moved to example 4, which I consider a level 3 problem. So, as always, I'm going to start by rewriting my equations above one another, lining up my variables. So I have 3x plus 4y equals 2, and 4x plus 5y equals 3. I needed to move the 4x to the other side in order to line up my variables. The reason why I consider this a level 3 problem is that there's no single number that I can multiply one equation by to create an additive inverse for x or for y. So I'm going to have to multiply each equation by a different number. I'm going to create an additive inverse for x. So I'm going to multiply my first equation by 4 to create the term 4x as my first term. And then I need the bottom equation to have a negative 12x to cancel with my positive 12x. So I'm going to multiply every term in the bottom equation by negative 3. Now I can see that I've created an additive inverse, so when I add my equations together, my x's are gone. I'm left with 1y equals negative 1. And I can plug that into one of my original equations to solve for x. And I get x equals 2. So my solution is 2, negative 1. And we should still check it in both of our equations. And it works in both equations, so I know that I got the correct solution. This is also the point of intersection, the only ordered pair that works in both this equation and this equation. Thanks for watching, and feel free to come in with questions tomorrow.